going to move into redox chem. This is super duper duper high yield in terms of this is like a whole topic in year 12. It's not even like a whole topic, it is a whole topic in year 12. You need to know how to do this really well, and they expect this stuff as basic knowledge going into year 12. So it's really important you know this stuff. So we're going to go through the basics today. We're not going to go through anything difficult. Now, redox can become really difficult, and I'll preface that in terms of the first time you learn redox, it's really difficult. So this may be the first time you're seeing it. If it's the first time you're seeing it, you may really struggle with it today. Don't expect to come out of it, knowing everything and being able to answer every single question that comes up. That's not necessarily going to happen. You just need to be aware that this can be quite difficult to sort of get your head around the first time. So what is redox? Well, it's a huge topic, super confusing. Many of you watching this lecture will have never touched it, so don't expect to be experts after today. We're going to move really slowly, and we're only going to cover the basics. We're not going to go into any sort of application-based stuff. That's going to be sort of left for the next set of lectures in sort of our spring lectures, because that'll be on the end of you guys already doing redox, so we're going to go through some really complex sort of application of it. Whereas today we just want to do the basics. The goal today is for you to have a small understanding of the basics, so when you go through in class again, it'll be easier to sort of put that jigsaw together. When your teacher's going through stuff and you going through concepts, you'll be like, oh, I've heard of that before. I've seen that before. I know sort of how to link those topics together, etc. So redox is basically a concept that involves the transfer of electrons. It's kind of like how we transfer money. Redox involves transferring electrons. Electrons are like the currency of our molecules. So red means reduction, ox means oxidation. These are the two key things that happen. We have reduction and oxidation. Without them, we don't have a redox equation. So cellular respiration to give you energy is an oxidation reaction. Combustion to keep you warm, or combustion, for your petrol in your car, redox reaction. Batteries in your phone, redox reactions. This is important for 3 and 4 chemistry. So all of these concepts can either happen in a direct or indirect way. As you can see here, this color changing is a direct reaction, and this is a redox reaction. So aqueous redox reactions, such as the traffic light reaction, often involve color change. And this is an example of a direct redox reaction. So, I don't know why the transitions went a bit weird there. That was my bad. I think I tried to put animations in that went a bit skew-if. Nonetheless, this is the basic building block of redox chemistry. Redox chemistry occurs in 2 parts, but the 2 parts must happen at the same time. Without one part, the other part doesn't happen. Full stop. If you don't have reduction, you don't have oxidation. Full stop. So, reduction and oxidation can be simplified down into what we refer to as oil rig. Oxidation involves loss. Oxidation involves loss. What does it lose? It loses electrons because they are the currency. Oxidation involves loss. Rig. Reduction involves gain. Reduction involves gain of electrons, because again, that's our currency. So as you can see here, here's some very brief general formula. So you have M, which is your original product, goes to, or comes back from, but we say it's going to go to because we're doing oxidation. So we're going to M plus, or M positive, plus an electron. What that means is the electron is lost. This electron can go wherever it wants now. It's free to do whatever it wants and leave. In our other equation here, so in our reduction equation, our electron has been free to do whatever it wants, and then it comes in here. Free to whatever it wants, and then it comes in here. And now, when it comes in here, it's now added into this molecule, and it's stuck in there. It's not free to go and do whatever it wants. So it's being gained. That electron has been gained. This electron has been lost. Left electron here, this one over here, has been lost. This electron here has been gained. So think of it like this. You've got A plus B. A's got an electron hanging around. They all do, but let's just got an electron hanging around. And then it goes, you know what? Maybe I will. Oh, I don't know why. Again, I think my animations are going a bit skew-if. That electron is going to go whoop, and go over here. So as you can see, these electrons move from one to the other, and they move across, and they make this A plus and B minus. As you can see, I think it was meant to in this. There was meant to be a transition for that to move, but it didn't move. So the electron moves across to our B minus. So the electron was lost from here, and A underwent oxidation. The electron was gained here, so B underwent reduction. Now, this is where the terminology gets really confusing, and you're going to take a few times to get your head around this, so don't expect to get your head around it straight away. Since A sent an electron to B and underwent oxidation itself, we call it the reductant, because it caused B to go through reduction. By sending that electron, it caused B to undergo reduction. Think of it as like the teacher teaches you. As much as the teacher, we call the teacher, but she's not taught, she's teaching you, or he is teaching you. Same thing here. It is sending the electron to B, and as such, when it sends the electron to B, it causes reduction. And so we call it the reductant, even though itself is undergoing oxidation. For B, we think that B pulled the electron. So we're saying B actually pulled the electron from A, and even though B itself underwent reduction because it gained that electron, it caused A to undergo oxidation by removing that electron from it. So we call B the oxidant. So this may be a better way of sort of seeing it. You'll notice in older exams they use oxidizing agent and reducing agent. It's old terminology, but it's still acceptable to be used. The oxidant is the species that causes oxidation but is itself reduced. I think but is a better word there because it sort of splits up these sentences really well. The reductant is the species that causes reduction but is itself oxidized. That's really, really important. So the reductant is the species, and oxidation is the process that the reductant undergoes. So remember this like this. I'll be honest, I don't remember it like that, but here's a little one that I know one of the other tutors uses, so I have been handing it out to my students for years. Some of them have found it really useful, but oxidant undergoes reduction, reductant is oxidized. You're welcome to utilize that if you want. I just find that it's easier to just sort of remember it and just say, hey, the oxidant causes oxidation but is itself reduced. So the other cool thing about sort of our redox reactions is that one does not happen without the other. That's really, really important. You cannot have reduction without oxidation, and you cannot have oxidation without reduction. And I want to continue to stress that. Reduction does not occur without oxidation. Oxidation does not occur without reduction. Reduction and oxidation will always occur together. You cannot have one without the other. Really, really important. Now, how do I identify that oxidation and reduction are occurring? Because I know electrons are moving, but how do I identify that? So, the way that you identify that is through what we call oxidation numbers. So, oxidation numbers may also be called oxidation states. So, these are used to determine if a reaction is redox. Think of oxidation states as imaginary charges, and we assign them to atoms in compounds. So this is where things get a little bit more complicated. There are a few rules. I'll go through the rules and then I'll show you how we apply those in sort of the question. So first step here, oxidation states of free elements. So Fe solid, that's a metal, sodium solid, chlorine gas, helium gas, these are all zero. These have no charge. They're free elements. They're not an ion. Therefore, they have no charge. They are zero. They are to zero. Oxidation states of simple ions, so Na positive, Cl minus, Mg2 plus, nitrogen 3 minus. These are equal to the charge of the ion. So Na plus has got an oxidation state of +1. Cl minus has got an oxidation state of -1. So these are sort of as they would be. In compounds, again, a little bit different. So in compounds, we have the main group metals have oxidation states equal to the charge of their ions, so Na plus Cl. and then Na will be Na plus, and then Cl will be Cl minus. So we're going to have +1 and -1. We have magnesium bromide. Bromide is -1. Magnesium is +2. So we're going to have +2 for our magnesium, and bromide is going to be -1. So even though overall this thing doesn't have a charge, we're thinking about it, there's 2 ions in there. Hydrogen is almost always +1, and oxygen is almost always -2. Now, there is one example. All right, I lied. There are multiple examples of hydrogen and multiple examples of oxygen that are not -2 or +1. However, they never come up. There's only one example that ever comes up in exams for hydrogen. There is no examples for oxygen that, actually no, that's a lie, it's the other way around. There are no examples for hydrogen that have or ever really come up. Oxygen has one example that comes up quite frequently where oxygen is not -2. So that's why we say hydrogen is almost always +1 and oxygen is almost always -2, because the examples that there are very infrequently or never used. But there is one example for oxygen that is frequently used. So the example is H2O2. Now, those of you who know what that molecule is, it's hydrogen peroxide. And for those of you who have heard of that before and are going, oh, where have I heard of that before? Think of like, you've probably watched like a World War II movie, and they typically portray it as sort of the Nazi spies, but it did happen on both sides, would have a hydrogen peroxide capsule put in them, put into their cheek, and then if they were ever captured, or it was usually put into a tooth, they would then break the tooth. That would, disperse into their mouth, and they would die pretty quickly. So hydrogen peroxide is a really, really deadly poison. It's not necessarily used as a poison, it is very deadly to humans, and thus we say it is a poison. In this case here, +1, -1. So overall, there's 2 of them, so it's +2, and you've got 2 oxygens, so it's -2, and they equal 0. But the individual oxygens in there are actually -1. It's one of the few examples you need to know, but you do need to know it. It does come up, so it's something you do need to know, and it's something I do want you all to sort of apply in your everyday sort of chemistry, that this one does come up, and remember it does. Otherwise, oxygen is always -2 and hydrogen is always +1. Sum of all the oxidation states must equal the charge of the species. So let's look at an example. We'll talk about an example that we've been through already, is that we went through earlier. We went through H3O+. Remember, we were working with this with our acids. We were talking about this all the time. Remember that this is always +1 and this is always -2. So overall, I've got +3 and I've got -2, and that equals +1. Well, it makes sense because my charge is +1. So that's sort of how I figure out what's going on. Now, in this one, we already knew that oxygen had to be -2 and hydrogen had to be +1. So it's pretty easy because we already knew that. If you didn't know it, you can then utilize that to figure out what's going on. So CO2, we have -2 for our oxygen. We're pretty comfortable with that. We know it's always -2. So overall, I have -4. Overall, this molecule is 0. So knowing that I have 0 and I've had -4 already because I've got 2 of those -2s means that this carbon needs to be +4. And there's only one of them, so the carbon itself is going to be +4. So I've now gone and figured out my oxidation states of all of my individual atoms just by simply knowing that overall my charge is 0. I have -2 for my oxygen, so therefore I'm going to have -4 for my 2 oxygens. And therefore, my +4s there, as you can see, there's only one carbon, so it's going to be +4. So that's sort of how you go about that one there. If I rub out my workings, I believe there should be already workings there. As you can see, it does it for me. It's a little bit laggy on my screen, I do apologize, but it will pop up eventually. So, moving forward, I don't know why this is full lagged out. Give me 1 second, everyone. Do apologize. This is the only way I can sort of share my iPad onto my computer because Apple doesn't have an innovative way of actually doing it. Don't know why it does that, Apple. All right, there we go. That was what I was trying to show you all. Let me move this back down to where it was before. There we go. Apologies. Then we have our PO4 3 negative. So our PO4 3 negative, as you can see here, We have an overall charge of, -3, and we've got oxygen, which is -2, and we've got 4 of them, so that's going to be -8. So -3, -8, what's the difference? It's 5 is the difference. So this is going to be +5, and therefore this is going to be +5. Now, if I get rid of all of that again, and then I go through and I go like this, you can see it's all there. Again, if it wants to load. Moving forward, they have H3O+, which we already just went through. I don't know why this is completely lagged out. I do apologize. Let me just keep doing this. If this continues to happen, I'll just change how I'm going about it, everyone. Sorry. I do have a cord here to be able to connect them. Sometimes it just happens to do this. The joys of Apple. But we've already been through this example, so we can just push through this one pretty quickly. All right, very good. So, how do oxidation states allow us to figure out if a redox reaction occurred? So, what we need to do is we need to find the oxidation state. So let's go through and have a look at the oxidation states of everything here. So what I've got here is I've got +2. What here I've got here is -1. What I've got here is +2 and -1. What I've got here is +1, -2, +1. I've got +1, -1. I've got +1, -1, +1, -2. I have 0. I have 0. I have +3, and I have -1. So, which of these is redox? For those of you who've never been through redox, you're going to have no idea. You're going to be sitting here like, how is this useful? What is going on? That is completely fair enough. As you have been through any redox, you would know by looking at this, which of these is redox? Well, it's the one with change. So which of these has change? The one that has change? Number 3. So, going through it. Not redox is the first one. Not redox the second one. Redox the third one. So, in the first two, there is no change in oxidation state. What that says to me is there's no movement of electrons. Electrons have not moved. So in these ones here, there is no electron movement. With no electron movement, this is not redox. In this last one, because there is significant electron movement, this is redox. It doesn't even need to be significant, just any movement. So, a reaction will only be redox if 2 or more atoms have a change in oxidation states. Really important, it needs to be 2 or more, but there's always going to be 2 or more. Like, you're never going to be provided one with 1 or more. With 1, sorry. If the oxidation state reduces, then the species was reduced. So, which of these was reduced here? Have a quick think. 3, 2, 1. It's the chlorines. So the Cls are reduced. And if the oxidation state increases, which of these were oxidized? Well, I don't even need to make you think because it's just the other one there. The aluminiums were oxidized. And it makes sense. Oxidation involves loss. Losing electrons means you lose negative charges because electrons are negative. So losing negative charges means your oxidation state should go up. Your Cls have gone down because they've gained electrons. Reduction involves gain. Gaining electrons, reduction, and you're going to have a decrease in your charge because you're gaining negative ions. So that's how that works there. So I want everyone to have a sort of a go at this question. Essentially, for those of you watching the live stream, I'm going to give you sort of 20 seconds just to think about this question. For those of you doing the recording, please feel free to just pause this and have a go. But this is a really good question that I want sort of everyone, including those watching the live stream, to do. So I am going to wait sort of 20 seconds. What happens to Fe2+ in the following reaction? Have a quick think. I'm going to give you 20 seconds. You can see at the top, we've got 20 seconds from now. Go. 24 past. We're going to do it. So, 10 more seconds. And done. All right. That's a very short amount of time. You'd obviously have way more time, but given we're doing a recording, I don't want to waste too much time. So what happens to Fe2 plus? Well, what have we got? We've got an oxidation state of +4, +2, +3, +3. So we've got Fe has gone from +2 to +3. Going from +2 to +3 means that, or what has occurred, we've had a gain of charge, but a loss of electrons, because we've lost an electron to gain a charge. So therefore we've lost electrons, has to be one of these two, process elimination, C or D, and then which involves loss? Oxidation involves loss. Therefore the answer here is C. This is a pretty straightforward type question, but it's a really good question to start off with. This is a really good question as you're starting off redox, because it sort of goes, all right, really basic concept, how do I go about it? What's my technique and my approach to a question like this when it's just the basics? This is a really good one for it. It involves oxidation, it involves loss, has to be C, it's not going to be A, B, or D. So, the overall redox reaction, as you can see here, we've got magnesium solid plus oxygen gas goes to MgO, can be split into two half reactions, which show the electrons moving. Remember oil rig? There are two half equations. We have oxidation and we have reduction. Remember those general formula that I showed you? The general formula all the way back here. Remember these? These are what we refer to as half equations. Now, half equations are really, really important. Half equations are theoretical ways of saying what's going on. Half equations in actual actual sense, like in an actual reaction and in the real world, don't occur. We don't see, we can't pull out a half equation from a full equation and say, all right, a half reaction. We can't even pull that out and say, all right, we just want the half reaction to occur, and then make some like vacuum where we just have the half reaction. It's not possible. Because why not? You need to have reduction and oxidation at the same time. So you're only ever going to see, when you do a redox equation in real life, you're only ever going to see the whole equation. That's all you're ever going to see. But we know that deep down what's happening is there's two half reactions occurring that form this one big reaction, which is all we see. So in this case here, our oxidation reaction would be Mg solid goes to Mg2 plus 2E minus. Because if we think about it, this was 0, and then this is 2 plus. So going from our sort of Mg0 to our Mg plus 2, and then here we have 0 and we go to -2, this has lost electrons because we've gained charge. So oxidation involves loss. Therefore, we're going to say, all right, the electrons are on the right side because, they're heading off. They're gone. But they're not actually going to head off. Where they're going is they're going, yeah, that's where the electrons are going. The electrons are moving down there. And when they move down there, what you see is that you get this electrons moving down, and you get this. I don't know why this is wrong, first of all. This one is wrong, by the way. Let me fix this second equation here. I don't know why this one is really wrong. But this is going to be O -2, and this is going to be, I believe it's going to be aqueous, and then this should be 2. This half equation down here is just wrong. I do apologize. But that is what it's going to look like there. So you're going to have the electrons actually flow around into here. And that's where that's going to go. So what is the best way of looking at these and learning about these half equations? Well, the best way of looking at these, because that one was really wrong, is going to your electrochemical series. Now, this will probably be the first major use of your chemistry data book that you're going to work with, because it's sort of the big hit the point, hit the mark sort of thing that you're going to do. So, if I scroll down to page 4, so it's one of the first couple of pages, you find figure 2 electrochemical series. So, the electrochemical series essentially has all these numbers here, which I don't want you to worry about for today. But the numbers we will talk about or you will talk about in class, and we will talk about it in our next set of lectures in spring. For now, these are not super relevant to you because they're sort of the next step on. So we're not going to worry about the numbers. what we're going to worry about is all of these half equations. As you can see here, these are all half equations. Now, all of these half equations are in the form of what's going on here. We're gaining electrons, so they're all reduction because we're gaining electrons. These are all produced as reduction equations. We can flip these and put like the Ni solid here, and then Ni2 plus 2E minus, and then therefore this would be oxidation. But they're all produced as reduction equations, so that would be oxidation. They're all reduction equations for now. So don't worry too much about it. These are just all oxidation equations for now. So in looking at that, what's going on here and why is the electrochemical series in this sort of order? So the electrochemical series is kind of cool because it is sort of different elements looking at how they react together. So we all know that things react differently. And so what we do is we rank elements based on how easily they oxidize or how easily they reduce. And we can look at that through our numbers. I don't want to worry about the numbers today. What I want to worry about is saying, all right, where are our strongest oxidants and where are our strongest reductants? Because remember we say the oxidant causes oxidation in our other species. Our reductant causes reduction in our other species. So if they cause it, which ones are the strongest oxidants and which ones are the strongest reductants? Which are the ones that are going to cause it more? It's like our sort of acids and bases, how we have strong acids, strong bases. They're more likely to accept or more likely to donate. Same thing, but here it's more likely to cause reduction, more likely to cause oxidation. Those concepts. So where are our strongest oxidants and where are our strongest oxidants and where are our strongest reductants? So given that this is a redox equation and this molecule here is going through redox, so this one here is going through redox, what do we think? Is this going to be an oxidant or a reductant? Because it's going through reduction. So have a quick think. Is this going to be an oxidant or reductant? It's going to be an oxidant. So this here is going to be an oxidant. And what I will tell you is that this is the strongest oxidant. Down here, this is the weakest oxidant. So what we can say, coming back to this page here, is that this is oxidant strength. So if that there is oxidant strength, which way do you think reductant strength goes? Given that these now on the other side are reductants. Well, if this down here doesn't want to go through oxidation, it's actually going to really want to go through reduction. So this is reductant strength. So oxidant strength goes up, reductant strength goes down. So there are other things on this I really want you to label. So the other things that I think are really key for us to label here today are our standard hydrogen electrode. Now, standard hydrogen electrode falls at 0. Now, just for context, this whole chemical series was made under SLC conditions, which we'll discuss in a second, and it was all made based on standardizing from here. So these values, these number values and everything that's sort of put in the order it is based upon how it reacted with the standard hydrogen cell. So the standard hydrogen cell is given 0 because it was the standard, it was used in the middle. The strongest and weakest oxidants, this is the strongest, this is the weakest. The strongest and weakest reductants, this is the weakest, this is the strongest. And then if you look through, there are a few other things that you could label, but I think for now this is all we really need to do. So this is a really cool series. It's really useful and you'll be able to use it in questions. We're probably not going to go through how you sort of utilize it fully in questions today. We're going to discuss it very briefly, but this is what you're going to use in a lot of your questions. So it's good to be familiar with it and familiar with how it sort of is set up, because it's set up in a very, very specific way. So looking at this, just quickly, because we did discuss this, SLC conditions. So SLC conditions are what we refer to as standard laboratory conditions. These are a set of standard conditions to ensure we control all potential variables. So these include having whatever you're doing at 25 degrees Celsius. Also, could be referred to as 298 Kelvin, because Kelvin, degrees Celsius, we know all about that now. If it is a gas, it needs to be at 100 kilopascals of pressure. So that is just a measurement of pressure. You need to be at 100 kilopascals. If it is a solution, it needs to be at 1 molar concentration. So what we're doing here is we're just trying to standardize. Think of a bit of experimental design. All we're trying to do is say, hey, if we make everything as sort of standard as possible and we minimize the potential sort of reactions that could occur, if we standardize things as best as possible, this is what we get. So if these conditions are not met for the redox experiment, we cannot utilize the electrochemical series. Really, really important. So if a question doesn't have everything at this, we cannot use the electrochemical series. So let's apply the concept. So we will do one little application of it. I want everyone to write out the half equations for the oxidation of zinc to zinc 2+, and then the reduction of Ag to Ag solid. So Ag plus to Ag solid. So for those of you who are watching the recording, please pause and have a go. We're just going to go jump straight into it. So I could go ahead and do this because they're fairly straightforward concepts. We have zinc solid, and it's going to zinc 2 plus aqueous. So where do I balance? Well, this is +2 and this is 0, so I'm going to add 2 electrons here. So what have we got? It's losing electrons, therefore this is oxidation. Happy with that. But there's an even simpler way of going about this. Most of these simple half equations are found, just here. Most of them are found in here. There is my zinc half equation. I just have to flip it around. The other one we were working with was Ag. Ag is up here at the top. Ag is just here. So I just need to copy that down. And because this one is actually going from Ag plus to Ag solid, unlike the last one, this one I can just copy straight out of the book. So goes Ag plus aqueous plus E minus. Now electrons don't have a state, really important, so don't put a state with them. Goes to Ag solid, and that was oxidation, so this is going to be reduction. So really important you sort of understand that you can use the electrochemical series to sort of obtain this information that may seem like these may seem like a little bit difficult at the start, but you can just go to electrochemical series and most of the time your answer's there. Now, the next step here is write the full equation. So how am I going to go about this? What is going to be involved in writing my full equation? Well, I need to add these two together. So I need to add them together. By adding them together, I need to eliminate my electrons. What's really important here is that this is 1 and that is 2. So I'm going to need to double this equation. So it's going to need to be 2, 2, 2, and 2. In doing that, that goes and that goes. They balance each other out. So my overall equation is going to be zinc solid plus 2 Ag plus aqueous goes to Zn2 plus aqueous plus 2 Ag solid. And that there is my full redox equation. That is what's going on there. So, as you can see here, I've removed my electrons by doubling the bottom equation. I've removed them because they cancel each other out, and then I have my full equation here. So, the last little concept, there's like 2 little concepts I want to go through before we finish off, and that is our production of half equations when they're not in the electrochemical series. So, when our half equations are not in our electrochemical series, things can seem a little bit difficult. You might get to the question and be like, oh lordy, what am I doing? This doesn't make sense. What's going on? I've checked my electrochemical series. I go here and I go and I scroll through and I'm like, oh, I can't find it here. What's going on? Why is this so difficult? That's because they're expecting you to create it. And sometimes they do expect you to create it. So how do we actually figure out the half equations if they are not in the chemical series? We use this method called COES. Now, COES stands for, each of those letters stands for something. So we have key elements, oxygen, hydrogen, electron states. So they each stand for a step. Now, the COES method involves 5 steps. Step 1, balance the key atoms. So realistically, the first step is to write down what's going on. So write down, what do you start with, what do you end with? Because that's what you're going to be given. You're going to be given, hey, this ends up in this, right? This is a half equation, like a half redox equation. And you're going to be like, I know this gets to this, but then what else is there? Where are the electrons? It's not showing me on the electrochemical series. What do I do? Go ahead and do the Coase method. So K. K is your key atoms. So all atoms except for hydrogen and oxygen need to be balanced first. So you need to balance them out. Second, balance your oxygens by adding H2Os to the side where there are less oxygens. So if you've got 2 oxygens on one side and no oxygens on the other, you're going to need to add 2 H2Os to that other side. The third step, balance your hydrogens. Now you balance your hydrogens by adding H+. So if there are 2 hydrogens, so maybe you added in 2 H2Os on this side because you had to balance out your oxygens, you now have 4 hydrogens here and you've got 0 hydrogens on this side. You're then going to have to add 4 hydrogens on this side because you have 4 here, so you need to add 4 H pluses here. You then add your electrons by balancing your charges. So you've gone and added H2Os here, which made you add hydrogens here. You added 4 of them. You've got 4 H plus here now. There's no other charges within this half equation, but you've got 4 H plus here. Therefore, you've got a charge of +4 here. You need to, and a charge of 0 on this side. You need to balance that out by adding 4 electrons to this side. So you go 4 plus to 0. And you go 0 to 4 plus, you add 4 electrons, you go from 4 plus here to 0 here. Lastly, you just need to, don't forget states. You just need to add in states. So you might see me at times forget to put states in. That's just because we're obviously not an exam or a stack right now, so I'm probably a little bit lazy in putting my states in. But it's really important to get into the habit of putting states with everything, because once you get to exams and stacks, it's really important you do put states in. If you continue to forget, you're going to continue to lose marks. So really important you go through that. So the best way to learn the Coase method is to go through an example. So we're going to slowly go through this example. For those of you who are at home, please have a go at this first. Please pause this video and just have a go. The first thing, well, before you pause, the first thing you're going to do is you're going to write out your atoms first. So you're going to say SO3 2 minus. Now give yourself some space. So give yourself some space and then write out SO4 2 minus. So you've given yourself some space. You've got space here to write and space here to write because you may have to put something in there. From here, I want you to have a go at this question. Use your Coase method. Think of each of your steps. Go, all right, I've got K, and then O, and then H, and then E, and then S, and go through each of these steps. So I want you to take your time and go through this question. So those of you at home watching the recording, please pause now. Those of you in the live stream, you're welcome to head off and have a go at this and then come back, but we're going to go through it right away. So start off with K, key elements. So what are our key elements here? Well, sulfur is our only one, and there is 1 sulfur on either side, so we don't need to balance. Cool. We can actually skip that step. 2, oxygen. Need to balance my oxygens. I have 3 here and I have 4 there, so I'm going to need to add 1 H2O here because I've got 2 on this side and I've got 1 on that side. So sorry, I had 4 on that side and I had 3 on this side. Therefore, I need to go from 4 to 4. I now have 4 and 4. Now I need to balance my hydrogens. So I added 2 hydrogens into the left. I've got none on the right, so I need to add 2 H plus. Now I need to balance my charges. So my electrons, my E. Balancing my charges, I've got -2. I've got -2 plus 2, so I've got 0. I need to add -2 to this side, so I'm going to need to add 2E minus. That is my overall equation. But remember the last step. Last step's one of the most important ones. Don't forget the states. So I don't want to forget the states here, so I'm going to add in an S, and I need to add in my states. So this will be aqueous. If you're not sure, it's always going to be aqueous. This is liquid. This is aqueous. This is always aqueous. And there's no charge, there's no state on your electrons. That is your overall equation. So we have just been through the Coase method, and we have just produced a half equation for this example here, which, if you go to this, it's not here. And the other really cool tip here to check that this is right is, if I look, I've gone from, this is -2, and this is -2, and I go, all right, this is, sorry, just get rid of these scribbles. So back to this, I've got -2, I got -2, therefore this is going to be -6, and it equals -2. I need this to be +4. Here, this is -8, and this is -2. So therefore I need this to be +6. So I've gone from +4 to +6. So +4 to +6 here. So where are we? We're at +4 to +6. +4 to +6. That is a loss of electrons. So it is oxidation. Oxidation involves loss. Oxidation has its electrons on the right because it always loses your electrons on the right. And as you can see, the electrons here are on the right. So it's another quick way of saying, all right, did I actually get this right? Did I do this half equation right? Well, I did, because my electrons are on the correct side. And that's like a good sort of second step to figure out if you've done everything correct. Now, we have talked about acids and bases. And what about our initial Coase method was acidic or basic? Have a quick think. 5, 4, 3, 2, 1. What do you think? What was acidic or basic about it? Well, it had H pluses added in. When you add in H pluses, what have we got? We got an acidic compound. We got an acidic solution. So the Coase method, we have been making an assumption that the reaction medium is acidic. Now, you are going to make this assumption no matter what if you are not told in a question if it's acidic or basic. So if you're not told in a question that your solution or your medium is acidic or basic, you assume it's acidic. You assume H pluses. Really, really important. You assume acidity. But what if instead you are told, and it's really important, you will be told the reaction medium is basic or alkaline? We need to add in an extra step. So we have our normal Coase method, which we've already been through. We add in an extra step. That extra step is adding in OH minus ions. So we cancel out the hydrogen ions by adding in OH ions. And this complicates this. So let's jump back to this example here. Let's go back through and get back to okay. So we're going to go back to this example. We're going to do this example again. And we're going to get rid of this. And we're going to do this example in orange. We're going to say, all right, SO3 to negative goes to SO4 to negative. So we're going to do this example again. This example is going to look like this. Again, balance our key atoms. Cool, we don't need to. Oxygens next. So add in our oxygens. H2O. Cool, happy with that. Balance our hydrogens. +2 H plus. Cool, happy with that. Extra H. So we've been through step 1, which was our K, step 2, which is our oxygen, step 3, which was our H. Now we're going to step 4, which is our extra H. So at this point, we're at our extra H step. This is our extra H. We need to add in hydroxides. Now, how many hydroxides am I going to be adding in? Because I want to balance this out. Well, I'm going to be adding in 2. So I'm going to be adding in 2 OH minus, and I'm going to be adding in 2 OH minus. You need to add it to both sides here. You can't add to one side because you're not balancing. In this one, you're neutralizing or cancelling out. By cancelling out, you need to add one into both sides. When you're balancing, you can just add to one side. This step, we're not balancing, we're cancelling out. Really important wording, as you can see here, really important wording. Balance, 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 balance. And these ones you can just add to one side and not add to the other. This step here is cancel, so you have to add to both sides when you cancel. So coming back, we have SO3 plus H2O plus 2 OH minus, and we have SO4 2 minus plus 2 H plus 2 OH minus. Now, how do these cancel out? These cancel out by going bang, bang, plus 2H2O. So now we have H2Os on both sides. Well, that's a bit useless. By having two H2Os on both sides, we then need to cancel out again. This goes and it becomes +1, and this one goes. Then what we need to do is go back to our equation and go, all right, we've done our extra H, now we're on to E. Electrons. Now, what do I have? I have a charge of -2. I have a charge of -2, -2, -4. I need this to get to -4 on the right side here, so I'm going to add another -2. By adding another -2, that is going to come from 2E minus. Now, then you go ahead and add your states. So this is going to be aqueous, 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 and liquid. The one thing that's really important about this method is if you've already done the acidic one and then you go and do the basic one, you need to make sure that you have the electrons in the same place, and usually it's the same amount. So same amount, same place. They're both on the right side, there's still oxidation, and you still have 2. Tick, that means I'm comfortable that I've done both my acidic and basic techniques correct. So I've correctly been able to adapt my acidic technique into a basic technique here. So that's a really key concept to be able to do. So, COs, acidic, you assume acidity unless told otherwise. So if your question doesn't mention an acidic environment or a basic environment, you do COs without the double H. You do the acidic version. Acidic is your base. You always, well, it's actually a really bad way of saying it. Your acidic is your fallback. It's your standard. You're always going to do acidic unless you are told it is basic or alkaline. If it is basic or alkaline, you add in the extra step.